Out that we have to talk about what's known as the Van Hoff factor, which takes into account that electrolytes often dissociate into multiple ions. And again, if all that matters is the overall number of particles, well, then this is going to directly impact the overall number of particles and is something we definitely got to take into account. And so this Van Hoff factor for strong electrolytes, it's just simply equal to the number of ions a particular strong electrolyte dissociates into. So if we take a look at NaCl, for instance, so NaCl is indeed a strong electrolyte, and a reminder, those strong electrolytes are either soluble ionic compounds, which is NaCl, or strong acids or strong bases, which you had to memorize back earlier in the course. And so in the case of NaCl, when it dissociates, you get 1 sodium and 1 chloride, a total of 2 ions. And so the Van Hoff factor here, we say is equal to 2, and we use this little lowercase I for that Van Hoff factor. Now, barium hydroxide is a strong base, and in this case, your strong bases were LiOH, NaOH, KOH, RbOH, CSOH, BaOH2, SrOH2, and CaOH2. And in this case, when it dissociates, you get 1 barium, you get 2 hydroxides. That's a total of 3 ions. And so the Van Hoff factor would equal 3. All right, now non-electrolytes, on the other hand, they have a Van Hoff factor of 1. They don't dissociate to give any additional increase in particles or anything like that, but they themselves are particles. And so you might recall that your non-electrolytes are typically molecular compounds that are not acids or bases. And so in this case, your molecular compounds are made of all non-metals, and this is methanol in this case, carbons, hydrogens, oxygen. And it's not an acid or base. It doesn't begin with like an H in the formula, like HF is a molecular compound that's an acid. Well, in this case, this is a molecular compound that's not an acid or a base, and it's therefore going to have a Van Hoff factor of just 1. No increase again in no increase in the number of particles due to dissociation or anything like that. So last but not least, we've got aluminum nitrate here, and I wanted to use one with a polyatomic ion because it's not necessarily the number of atoms something dissociates into, but the number of ions. And you got to remember that like with something like aluminum nitrate, you're going to get aluminum ions, but you're also going to get nitrate ions. But the nitrate ions themselves don't break apart into like nitrogens and oxygens and things of this sort. And you're going to get 1 aluminum ion, but you're going to get 3 of these nitrate ions for a total of 4 ions. And so for aluminum nitrate, this Van Hoff factor equals 4. And so it turns out, if you've got, 1 mole of methanol in water and 1 mole of aluminum nitrate in water, well, with the aluminum nitrate, you'd have 4 times as many moles of particles and 4 times the change in whatever colligative property you might be looking at. And so that's why these directly affect the number of particles in solution and are going to have a huge impact on how we look at these and calculate these colligative properties.